Hello, welcome to Maths with EJD. In this video, I'll be solving a two-part question bordering on metric spaces. And of course, the very first question is this. When is a metric? When is a metric space? When is a metric space said to be 1, complete, 2, compact, and 3, bounded? So that's the first part of the question. So let's move on to talk about this. So the first one is this, right? We are talking about completeness. Okay. And for completeness, right, you can say that a metric space X, comma D. X is the space, right? Whether it's a real number or anything, mostly real number, right? And then D is the metric itself. That's a distance function. So a metric space X, comma D is said to be complete. Is said to be complete if every Cauchy sequence, every Cauchy sequence in X, that is in this space, right? Every Cauchy sequence in X converges to a point, in X. So it means if you pick any sequence in this space, so that sequence also converges to a value inside of that X. So that is where you say it is complete. Of course, I know you're already wondering what a Cauchy sequence is most likely. So let's talk about that. So in other words, right? In other words, if a sequence xn, if a sequence xn in X is Cauchy. Cauchy means this, that is, its terms get arbitrarily close. Its terms get arbitrarily close to each other as the sequence progresses. As the sequence progresses. So, if you take a sequence and then as the terms are going on, then they get really very close together. Then that's when you see the sequence is Cauchy. So as the sequence progresses, that's what a Cauchy sequence means. Then there exists a point. There exists a point X in X such that the sequence converges to X. The sequence converges to X. Okay, talking about Cauchy sequence, right? You may want to it's been interesting to know that the sequence xn equals 1 over n is a very good example of Cauchy sequence. The idea of Cauchy sequence is that as the terms are progressing, the values are getting really close. Now look at this. So if you have sequence 1 over n, of course we know that's from n equals 1 to infinity, n equals 1 to infinity. So if we start from 1, that's 1 over 1, you have 1. Then you have 1 over 2, that's 0.5. 1 over 3, that's 0.33. 1 over 4, you have 0.25. That's 1 over 4, right? 1 over 5, 0.2. Then 1 over 6, 0.16. And you see, as you're going, the values are getting closer and closer together. The difference between this and this, for instance, is 0.5. Between this and this, it's now like, I think 0.17, right? Yeah, 0.17. And between this and this, it's 0.11, right? And between this and this, it's like 0.05. So you can see that as the numbers are progressing, right, the values in the sequence are getting really close together. That's why 1 over n is a very good example of a Cauchy sequence. All right, so that's very important to know. So that's what you need to know about completeness. So a metric space X, comma D is said to be complete if every Cauchy sequence in X converges to a point in that X where you take it from. Okay. So then I've told you about Cauchy that as the terms are going on, the values in the sequence, the terms in the sequence get very close together. Okay. So let's take the next one, which is about the next one is about compactness. Compactness. So let's talk about compactness now. Okay. Roman figure 2, I believe. Yeah. Roman figure 2 is about compactness. 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 So what do we say about compactness? Again, we say that a metric space X, comma D is said to be compact. Is said to be compact. Compact if every open cover of X, has a finite subcover. Of course, some new terms are getting thrown up, but trust me to explain them also. So a metric space XD is said to be compact if every open cover of X has a finite subcover. That's the first statement, right? So a metric space XD is said to be compact if every open cover of X has a finite subcover. But of course, you need to understand the other terms, right? You need to know that an open cover, right, is a collection of open sets. You know, we've already if you look at previous videos, we talked about open sets. Okay, so an open cover is a collection of open sets whose union contains X. Whose union contains X. So you may want to refer to the definition of an open set, right? And like that. So, of course, that we are talking about. So you see the idea of open cover coming up and finite cover. So we have to talk about that. So an open cover is a collection of open sets whose union contains X. That is X in the metric space. All right. Then talking about a finite subcover, right? A finite subcover, is a finite subset, subset, is a finite subset of the open cover that still covers X. That still covers X. So in other words, right? In other words, we can say that compactness implies that the space is small. The space is small, you know, in quotes, is small in some sense. In some sense. And every sequence X and every sequence in X has a convergent subsequence, Okay, so that's about compactness. And lastly, we talk about boundedness. When do you say that a metric space is bounded? Okay, of course, that sounds already, it means it has boundaries, right? So, but in the sense of, in mathematical sense, right, that we need to talk about that. Okay, so let's talk about boundedness. Okay, so talking about boundedness, right? Again, you can say a metric space, a metric space X, comma D is said to be bounded, if there exists a real number, so a real number m, such that the distance, the distance between any two, metric space is all about distance, right? Distance between points, any 2 points x and y in x, right? Is less than m. Is less than m. That means it doesn't ever surpass m. In fact, it's not never up to m, because m is m is m is up there, so to speak. That is d of x comma y. Of course, the metric d of x comma y is always less than m. So no matter how hard you try, you don't get to that m. And that is true for all x, y in x. Okay. So in other words, if you like, in other words, x is contained, in a ball, of finite radius, That's the idea of boundedness. So there's a particular value m that the distance function does not ever exceed. When you operate the distance function on 2 points, doesn't ever exceed that. Okay, so that takes care of the first part of the question. So now let's move on to the second part. Okay, let me switch up the markers. Let's say I go for this now, and then I have this to be this. Okay. All right. So the second part of the question, which is B, right? So okay, let me do this. B. Consider the space. Consider the space y equals 0, comma 1. So this is like a half open, half closed space. So what this means is that 0 is not part of these things, but 1 is part, because it's open below, meaning that it's excluding 0, but it's closed above, meaning that it contains 1. All right. So consider the space y equals 0, comma y, 0, comma 1 as a subspace, the subspace of the real number of R, right? Which is the real numbers, right? The reals. When y is endowed, with the subspace metric, with a subspace metric. All right. Then the sequence, xn, which is then the sequence xn, which is n equals 1 to infinity, right, is clearly a sequence in y, is clearly a sequence in y. So the question is to verify if y is complete. Verify if y is complete or not, Stating clearly your reasons. Your reasons. So first of all, we're talking about completeness here. So you definitely want to refer to the definition of completeness that we talked about earlier, right? That we said that a metric space x of d, x comma d is said to be complete if every Cauchy sequence in x converges to a point in x. So if you pick any Cauchy sequence in that space, so it always converges to a value in that x. So let's look at this case and see how we can go about this. Okay, so we go. All right. So to determine whether the space y, which is 0, comma y, half open, half closed, open below, closed above, with the subspace, with the subspace metric, with the subspace metric is complete or not, is complete or is complete or not. So we need to consider a Cauchy sequence. We need to consider a Cauchy sequence in Y, a Cauchy sequence in Y, and check if it converges, to a point, in Y. That's what we have to do, right? Okay, so let's move on and consider a particular Cauchy sequence. So let's consider the sequence, that popular sequence I told you about before. Let's consider the sequence, which is xn, n equals 1 to infinity, defined by xn equals 1 over n. So we look at this particular Cauchy sequence. So we have established previously that it is actually Cauchy because as the values progress, the distance between consecutive values becomes smaller and smaller. That's why it's Cauchy, right? So let's consider this, right? So if we are to consider that, we see that this sequence is a Cauchy sequence. This sequence is a Cauchy sequence in Y because for any small epsilon greater than 0, right? That whenever we use epsilon greater than 0 in math, it means a very small number, but that is positive, like maybe 0.00001, it's very tiny, small number. So for any epsilon greater than 0, there exists an integer, n, right? N, such that for all m and for all mn that is greater than that particular n, right? So we have the absolute value of xm minus xn. That's consecutive terms, right? The difference between them is equal to the absolute value of m 1 minus 1 over m over 1 minus n, and that is always less than that epsilon, that small number. So as the values keep going, right, the distance between them is always is getting smaller. Since this is already a small number, the difference between consecutive terms in this 1 over n thing that we talked about, right, the distance between them is getting smaller and smaller, such that for each consecutive 1 over n you take, the distance between them is less than that very tiny number epsilon already. Okay, so in that case now say since, okay, let me change the color at this point. So we can say since 1 over m minus 1 over n is less than epsilon, all right, for m comma n greater than 1 over epsilon. So we can say that the sequence xn is Cauchy. All right. So I demonstrated that already before, that if you have 1 over n, right, moving from n equals 1 to infinity. Okay, if you put 1, you get 1. If you put 2, you get 1 over 2. I mean, to see it better, it's 0 0.5. 1 over 3, you get 0 0.33. 1 over 4, 0 0.25. 1 over 6, 1 over 5, 0 0.2. 1 over 6, I think 0 0.16, and it goes on like that. So you see that as all these things are happening, the gap between consecutive values is getting smaller and smaller. Okay, this is 0 0.5. The second one is 0 0.17. See the fast depletion. The next thing is like 0 0.11, I believe. The next one is like 0 0.05, moving so fast. And it's like 0 0.05. 4. So, and then, it just keeps reducing like that. So that's what makes it coachy. Of course, since you are proving this is just an aside, it's not supposed to be part of it. Because everything we have here this is just a demonstration of what has been said up there, right? Okay, so now that we have that, now you see that as this value is going, one day if it gets to infinity, right, it's like 1 over infinity, and 1 over infinity is 0. So it means that this expression is actually going to converge towards 0 ultimately. All right, it's going to be approaching 0. As you can see already, the numbers are moving so fast towards 0. Okay. So in that case now, we can now say, however, however, the sequence xn, which we have established to be Cauchy already, the sequence xn converges to 0, converges to 0, converges to 0, which I just explained now, which is not in y, which is not in y. You already remember that y is 0, comma 1. So because it is open here, it means that 0 is excluded from this collection. Because it is closed at the top, 1 is involved. So you see, 1 over n converges to 0. And then that thing it converges to, which is 0, is not in this space. So you see, it's in that way, it is not complete, because completeness means that if you take any sequence, any Cauchy sequence within the space, so that Cauchy sequence will converge to a value within that space. So, and in this space, you have, 0 is excluded. So as that 1 over n is converging to 0, which is not part of the y we are looking at, then you can say the sequence is incomplete. So you see 0, which is not in y, all right? Because 0 is not in the set, because 0 is not in the set 0, comma 1, because it's excluded like that, right? So we can say therefore y, which is 0, comma 1, is not complete, is not complete under the subspace metric, And that brings us to the end of that two-part question. So if you have not signed up to this channel, you want to do that, you want to hit the notification bell so you can get alerted anytime I upload a new video. You also want to comment, share, and like. For instance, this question is actually from one of my viewers who would like clarity on this. So keep your questions coming, keep the likes and comments coming, keep the subscriptions coming, share with others, because it will definitely be helpful. So see you in the next video. Thank you so much for always coming by.